All right, in this section we're going to see something called the unit circle, which turns out to be a very useful way of organizing radian and degree angles and their trigonometric values. So, what is the unit circle? The unit circle is simply a circle with radius 1. When we talk about the unit circle, we're referring to the circle with radius 1 centered at the origin. So let's pick a point on the unit circle, and let's call it xy. Because this is a unit circle, it means the radius is 1, so this particular length is 1. Now, we've seen this situation before when we were defining the trigonometric functions. We can build a little triangle here, and we can define this horizontal length to be x and this vertical length to be y, which gives the address of the point xy. We can call the angle down here theta. And we know this arc length here, which we can call s, is going to be equal to r times theta. Since we know the arc length formula, s is r theta. But in this case, r is equal to 1, so really we have s is equal to theta. So when we talk about the trig functions of the angle theta, it's perfectly reasonable and fair to talk about the trig functions of the arc length s. So we could talk about sine, cosine, tangent of s, because s has exactly the same measure as theta, as long as theta is in radians. Okay, well, let's talk about the trig functions for a moment. Let's notice something. We know that sine of theta is defined to be y over r. Okay, we can make a few refinements right now. First of all, we don't need the theta. We can use the length s. Call it sine of s, since s is equal to theta. Also, because this is a unit circle, we know r is equal to 1, which means we can just say sine of s is equal to y over 1 instead of y over r. But that's just y. So sine of s is simply equal to the length y. Similarly, cosine of theta, we could say, well, we know that's x over r, but by the same reasoning, we could write this as cosine of s is equal to x over 1, right? So x. Tangent of s is still y over x. And now cosecant of s is 1 over y. Secant of s would be 1 over x, the reciprocal of just x. And cotangent of s would be x over y. So, great. This doesn't seem particularly groundbreaking until we go back to the unit circle, and we note that any point on the unit circle is labeled xy. Okay, but since x is equal to cosine of s and y is equal to sine of s, that actually means that any point on the unit circle can be labeled as cosine and sine of the arc length. Or, if you wish, cosine of the angle and sine of the angle. This means that for our special angles, all we have to do is look them up on a very specific unit circle, and we can read the trig function values off of the xy coordinates of the unit circle. Okay, so let's build a bigger and better unit circle that has all the good information that we want. Okay, so we're going to now construct what is classically regarded as the unit circle. I do very strongly recommend that you learn how to build this model itself. You don't need to build the entire unit circle. I will show you how you can build just the parts that you need as you need them, but we are going to build the whole one right here. Okay, so we're going to claim this is a unit circle. which means this point right here has the coordinates 1, 0, because it's 1 unit from the origin there. And this guy right here will have the coordinate 0, 1. This guy right here, -1, 0. And this guy down here, 0, -1. Now remember, the coordinates are in the order of cosine of s and sine of s. So right away, if we're measuring in radians, we can see various cosine and sine values. So in standard position, this point right here is 0 radians. And this point over on this side is pi radians, because we know pi is 180 degrees. So we can see right away that cosine of pi is -1 and sine of pi is 0. All right, or equivalently, cosine of 180 degrees is -1, sine of 180 degrees is 0. Okay, up here we have, in radians, pi over 2. It's halfway to pi. It's also 90 degrees. And we know cosine of pi over 2, or cosine of 90 degrees, is 0. And sine of pi over 2, or sine of 90 degrees, is 1. So you see right away we get information very quickly that we used to have to work to find. Working our way around the circle, we can get, in radians, 3 pi over 2, which is down here. And again, cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is -1. Okay, well, what we'd like to do is fill this with all the intermediate values for all the special angles that we know and love. So let's start with the ones that are perfectly diagonal. This would be pi over 4, because it's 1/4 of the way of a semicircle. And the one over here would be 3 pi over 4, as it's 3/4 of the way of a semicircle. You can also think of this as 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is pi, 5 pi over 4, 6 pi over 4, which is 3 pi over 2, and 7 pi over 4. Then if we kept going, we would get to 8 pi over 4, but that's 2 pi, which is coterminal to 0. So we're going to find the coordinates here. Now, we know in degrees that pi over 4 is 45 degrees. So these coordinates here we're going to populate because we know what cosine and sine of 45 degrees are. We can look them up on a 45, 45, 90 triangle. Well, we know that cosine of 45 degrees is root 2 over 2, and sine of 45 degrees is also root 2 over 2. Okay, let's keep our attention on the first quadrant for just a moment. We also have as special angles pi over 6, which is 30 degrees, and pi over 3, which is 60 degrees. We know that cosine of pi over 6 is root 3 over 2, and we know that sine of pi over 6 is 1/2. We can confirm this by, again, looking these up on a 30, 60, 90 triangle. We know that cosine of 60 degrees is 1/2, and we know that sine of 60 degrees is rad 3 over 2. If we go to the second quadrant, we can find these corresponding angles over here and here. And we're going to see that if we're counting by pi's over 3, we have pi over 3, and then over here 2 pi over 3, which is twice that amount. Let's keep going. 3 pi over 3 is pi. That's already counted. 4 pi over 3 would be right down here. And then 5 pi over 3 would be right here. Okay, let's count by pi over 6's now. We have 1 pi over 6, 2 pi over 6, which is pi over 3, already counted, 3 pi over 6, 4 pi over 6, 5 pi over 6, that would be right here, 6 pi over 6, that's pi, 7 pi over 6, 8 pi over 6, which is 4 pi over 3, 9 pi over 6, 10 pi over 6, next would be 11 pi over 6, and this is actually the last one, and finally 12 pi over 6, which is 2 pi, and that's coterminal to 0, so we've made it all the way around. Okay, so what are the actual coordinates here, here, and here? Well, they're going to just be a simple reflection of the coordinates for the first quadrant. So if you understand how the first quadrant's laid out, you can reflect. So this 2 pi over 3 has the same denominator as the pi over 3 here, so it's going to inherit its coordinates. And we're going to have 1/2 and rad 3 over 2. However, in the second quadrant, x values are all negative. Y values, of course, remain positive there. So this coordinate pair, which is a 3 pi over 4, will be a reflection of the pi over 4 guy. So that's rad 2 over 2, rad 2 over 2. The x will be negative, though. This 5 pi over 6 will be a reflection of the pi over 6 one. So that'll be rad 3 over 2 and 1/2. Oh, but the x is negative. So if you were asked, what is cosine of 5 pi over 6? Well, we know that that's cosine, the first coordinate here. So cosine of 5 pi over 6 is negative rad 3 over 2. Okay, we'll do the same thing here. So 7 pi over 6 is part of the pi over 6 family. So it's going to be rad 3 over 2 and 1/2. But in the third quadrant, everything's negative. So this will be negative rad 3 over 2, negative 1/2. 5 pi over 4 is part of the pi over 4 family. So it's negative rad 2 over 2, negative rad 2 over 2. And 4 pi over 3 is from the pi over 3 family. So it's going to be negative 1/2, negative rad 3 over 2. And finally, we'll label these coordinates, and then we're done our unit circle. So 5 pi over 3 is part of the pi over 3 family, so it's 1/2 and rad 3 over 2. But y values are negative in the fourth quadrant, so this is negative rad 3 over 2. 7 pi over 4 is part of the pi over 4 family, so it's rad 2 over 2, rad 2 over 2, except the y value will be negative. And 11 pi over 6 is from the pi over 6 family, so we have rad 3 over 2 and negative 1/2. Okay, you can see that all the signs are correct in the sense that in the fourth quadrant, for instance, we have cosine values which are positive and sine values are negative. In the third quadrant, both sine and cosine values are negative. In the second quadrant, cosine values are negative and sine values are positive. This is everything we would expect, right? And in the first quadrant, of course, everything's positive like we want. Very good. All right, so we're going to use the unit circle to work out some examples. Let's suppose we're given, say, cosine of 3 pi over 4. Well, we simply locate 3 pi over 4 on the unit circle and read off its cosine value, which is its first coordinate. So that's negative rad 2 over 2. Isn't that great? Okay, how about sine of 7 pi over 4? Again, we locate 7 pi over 4 on the unit circle and read off its sine value, which is its second coordinate. So that's also negative rad 2 over 2. Simple as that. All right, what about tangent of 5 pi over 4? Well, we locate 5 pi over 4 on the unit circle, and we would want to read off its tangent value, except the coordinates only tell us cosine and sine. So no problem. We know tangent is y over x, or sine over cosine if you wish. So we could simply take the y value and divide it by the x value. Well, those are exactly the same thing. So something over itself evaluates to 1. So tangent of 5 pi over 4 is equal to 1. All right. So let's make a quick observation here. Notice that all the pi over 4s occur right in the middle of their quadrants. They're the diagonals. Those are the 45 degrees equivalent. And notice that for all the pi over 4s, the coordinate pairs consist only of root 2 over 2. So if you're ever looking for sine, cosine, tangent, whatever, of a pi over 4 multiple, you know that the coordinate involved is going to be some version of root 2 over 2, root 2 over 2, with the quadrant determining whether or not each coordinate is positive or negative. So in the third quadrant, of course, everything's negative. For the family of pi over 6s and pi over 3s, notice that the coordinates consist only of some combination of 1/2 and rad 3 over 2. Let's look at, say, sine of 7 pi over 6. So we'll locate 7 pi over 6, and we can see that sine, being the y-coordinate, will be negative 1/2. So sine of 7 pi over 6 is indeed negative 1/2. Now, if you've got a unit circle in front of you, this is great. But we also need to learn how we can figure out these values without having an entire unit circle in front of us. The key is learning where these angles are located. So when you come across 7 pi over 6, you know that it's right here. If you can learn the location of the angles, then it's actually really easy to come up with these values. I'll explain how to do that in just a moment. But let's first even show you that quadrantals are easy. For instance, how about cosine of 3 pi over 2? Well, we can locate 3 pi over 2, which is right here. And cosine value is the first coordinate, so that's 0. How about tangent of pi over 2? Okay, well, pi over 2 is right here. Tangent will be y divided by x, so we would go 1 divided by 0. Oh, well, we know we can't do that. So we'll just say that tangent of pi over 2 is undefined. What about something that's not quite listed? How about sine of negative pi over 3? Well, we can just read pi over 3 this way and see that that's this coordinate point right here. So it's equivalent to sine of 5 pi over 3, which means we're going to use this y value of negative rad 3 over 2. What about cosine of negative 3 pi? Okay, well, again, we're reading negative. So negative pi gets us all the way to here. Negative 2 pi gets us back over here. And negative 3 pi gets us back over here. So it's going to be the coordinates off of negative 1, 0, and it's the x coordinate off of that. So our answer is negative 1. Okay, well, how would we evaluate a trig function value using the unit circle, but without the unit circle in front of us? So sine of 5 pi over 6. Well, let's locate 5 pi over 6. And this is why I stressed earlier that you should at least learn where the angles are located. 5 pi over 6 we know is in the second quadrant, and it's down here. And in fact, it's important that we draw it mostly in its right spot, which means we don't want to draw it here in the middle, and we certainly don't want to draw it up here. The pi over 6's are very close to the x-axis. So for instance, here's 5 pi over 6, down here would be 7 pi over 6, and then we have a bunch of pi over 4's and pi over 3's and pi over 2's until we get all the way over here, which is 11 pi over 6. And then over here was, of course, pi over 6. So those guys are never very far from the x-axis. All right, so we've got our 5 pi over 6 here. Now we need to determine these coordinates. Now the pi over 6's and the pi over 3's consist of some combination of these two numbers right here, 1/2 and rad 3 over 2. The question is, in what order do they go? Well, notice that 5 pi over 6 has a very small y value, but a very large x value. That means its y value, which is small, will be 1/2, and its x value, which is big, will be the big number, rad 3 over 2. And of course, the x value is negative. So just like that, we have generated the correct point. And if we want sine of 5 pi over 6, we can now read it right off of that. It's 1/2. You can also read cosine, which is negative rad 3 over 2. Okay, what about tangent of 4 pi over 3? Well, again, it's worth knowing where 4 pi over 3 is located on the unit circle. This is located in the third quadrant. The pi over 3's are the points that are pretty close to the y-axis. So this is 4 pi over 3 here. Okay, so we just need to label the coordinates here. Since it's a pi over 3 and or a pi over 6, it's going to consist of these numbers 1/2 and rad 3 over 2 in some order. Okay, but we can see there's a very small x value and a very large y value. So our y value will be the bigger number, and the x value will be the smaller number. And because we're in the third quadrant, they're both negative. Just like that, we now can read sine, cosine, etc. What we want is tangent, and tangent we know is y over x. So that's going to be negative rad 3 over 2 divided by negative 1 over 2. Notice that we can just always throw away these 1/2s, so I'm not even going to consider them anymore when we're working out tangent values. Here, of course, we're going to get positive rad 3, and that is the correct answer. Now, I want to stress that I'm not here to force you into a particular method. If you're perfectly happy taking this 4 pi over 3 and going, well, 4 pi over 3 is 4 pi over 3's, right, which is 4 times 60 degrees, because pi over 3 is 60, which is 240. So tangent of 240 is, in the third quadrant, going to be exactly equal to tangent of its reference angle because it's positive. The reference angle is 60, and now you call up a 30, 60, 90 triangle, and opposite over adjacent is rad 3 over 1, so you get your answer of rad 3. You can do that. I'm perfectly happy with you doing that. What I ask for is that you just have a way. You have a way of taking a question like this and arriving at this answer, and that way doesn't involve looking anything up on a computer or looking anything up on a table. This way of evaluating it by calling up the specific part of the unit circle that you need is what I believe to be the most efficient way of starting from a question like this and arriving at its ratio. Okay, let's do one more. How about cosecant of negative 9 pi over 4? Now, 9 pi over 4, indeed even negative 9 pi over 4, you won't find listed on a unit circle. The unit circle goes only up to 2 pi, and this is well past that. So what we're going to do is we're going to count out to it, because we understand that the pi over 4's are the diagonals in each quadrant. So let's count to negative 9, and remember we're going to go clockwise because this is a negative angle. So we'll start at 0. There's an angle of 0 radians, negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4, which is negative pi, negative 5 pi over 4, negative 6 pi over 4, negative 7 pi over 4, negative 8 pi over 4, and finally, negative 9 pi over 4. That's the guy we want right there. So those are the coordinates we're after for that specific point right there. Since it's a perfect diagonal, we know it's going to consist of the root 2 over 2's. So this is root 2 over 2 and root 2 over 2, except the y is negative because we're in the fourth quadrant. Okay, so we know this is the reciprocal of sine. And sine, we can see, is negative rad 2 over 2. So this is simply negative 2 over rad 2, the reciprocal of sine. If you rationalize this, multiplying the top and bottom by rad 2, you'll get negative 2 rad 2 over 2. And you indeed actually just get an answer of negative rad 2. All right, so that constitutes our conversation on the unit circle and how to use it.